So this is our session 6 for the foundation design course, in which we will be modeling and designing the wall footing for 3-story commercial building, right? And these are the contents for this modeling and design, in which we will be finding the sizes of the footing, and then we will decide the thickness, and then we will design the reinforcement for the wall footing. This is also called the strip footing. So if you learn the design for this wall footing, which is also called a strip footing, you can also design this strip footing for the RC or frame structure as well, other than residential building, because the procedures and all things are the same. Only the only thing that you have to check is the punching check. For the wall footing, there is no need to check the punching, right? So there will be no punching in case of the wall footing, right? So before starting with the size of the footing, let me show you the model for which we will be designing our wall footing. So this is a typical 3-story residential building, right? In which this is the car porch, and this is the lounge area, and these are the different rooms. And this is the 3D for the 3-story commercial building, in which the wall you are seeing, these are the brick masonry walls, and we are directly getting the loads coming from these slab and the walls on the foundation. We will be designing that. If I show you the material properties for the masonry, which I have defined, this is a 2000 psi, and you have to assign this. You can see this is a masonry, and the ETAB do not have the capability to design unconfined brick masonry for you. It designed the confined brick masonry for you, as you can design the confined brick masonry, in which it will give you the reinforcement needed inside or in between the junction of the walls, right? So we will not designing the brick masonry walls, but we want the loads coming from the walls or coming from the superstructure like slabs and beams and loads above it. We need that, right? Like I have shown the loads previously, we have also applied the load that is 40 live and 30 SDL for 3-inch thick tiles, marbles, whatever you want to place on the floors. So these loads has been applied on these floors, and the superstructure has been designed. Now our purpose or our job is to design the footing for this, right? So the main idea is the same, to calculate the sizes of the footing, like which we did in the combined footing or the associated footing, that you have to first of all check the minimum sizes, which is based on, again, the unfactored load, which is the service load combination, which you have to define in your ETAB model, right? And the size of the footing, again, you have to find it from the allowable bearing capacity. And for this, you have to find the total maximum service load. This is the first step on the walls or coming from the wall, or that is coming from the slab into the walls and then to the foundation and kips, and some all of that reactions coming from the wall, right? So what does it mean? It means you have to go to the base. This is the base, and I have shown the reaction. This is the reaction. These are the service load combo reactions, and these are the reaction of the walls, right? These are not the columns. These 2 or 3 are the columns, which is the car porch columns. We are not interested in that, but if you are doing the residential building, we have to design isolated footing for this, and strip or wall footing for this. How to design the isolated footing, you already know that, so we're not going towards this. So for the strip footing or wall footing, if you learn the design of the wall footing for this building, you can also design the strip footing for the residential building like RC building, or for the commercial building plazas as well. For example, in the last session, we designed the combined footing for the 3-story commercial building, right? So if you want to design the strip footing for that plaza, the procedure is same. How do you decide the strip and what will be the width of the strip? So you will learn in this session, and you can apply on the RC building or plazas as well, right? So the procedure for the strip footing is that you have to calculate the length of the strip you want to provide, and from the length you have to calculate the width, the required width to transfer the load into the soil, right? So for the interior walls, you have to calculate it separately, and for the exterior you have to calculate it separately, right? So for the interior, you have to sum up all of these reactions. For example, this is the interior wall. For example, let me show you in the plane. These are the interior walls, right? This is 1, 2, 3, and in the other direction, and these are the exterior walls. So you have to sum up the reaction of each, these interior walls, this wall, these walls, right? And you have to sum all of the reactions, and then you have to calculate the available length of the strip. For example, length of this strip, you will provide length of this strip, this, and this, right? So you have to calculate this. For example, it is available of like 16, 3 times 16, this is the length, right? And this 2 times 16, and then 2 times 12. So this is the total available length available for the interior walls to be transfer the load using the strip footing, right? So for this, you have to sum all of these reactions. For example, this is the interior wall, so you have to sum all of these reactions, these reaction, and these reaction, and you have to sum up all of these interior wall reactions, right? So let us go back to the presentation. From the ETAB result, I have already summed up the interior wall reaction, which comes out to be 750 kips. These are from the interior walls. You can also do the practice when I share the file with you. And this is the P2, which is the exterior wall reactions. And how do you calculate that? Because there are too many reactions, right? So once you have calculated these interior wall reactions, right? So you have to sum this reaction with the column reactions, right? And then you have to subtract it with the total reaction coming from the superstructure, right? So the total service load on the reaction, we have to check it in here, which I have already shown to you. How do you calculate that? You have to go to the tables and go to the analysis, results, reactions, and base reactions, right? So from the base reaction, this is the total service load coming from the superstructure. This is the service, and it is 950, right? So 950 is the total service load, right? So this is 1950. This is the total load in kip of the structure. And for the interior walls, the reactions were 750. So you have to subtract the 750 from the total load, and then subtract the column reactions, these reactions, from the total load. So this will comes out to be 1164. So this 1164 will become the reaction for the exterior walls. This is the procedure. How do you calculate the reaction for the interior of the exterior walls, right? So this is the overall procedure to calculate the reaction for the interior and exterior walls, right? So the next step is the allowable bearing capacity of the soil. Normally for a residential building, the soil test is not carried out. So the designer take the bearing capacity equal to 1 TSF, 1 ton per square foot, which is equal to 2.204 kip per square foot, right? So once you decide the bearing capacity, or if you have done any tests, you can take the bearing capacity from that. So the third step is to find the footing area, right? So for the interior walls, the total length of the strip available is 116 feet. How did I calculate this? I have already explained it to you, that we have to sum all of the lengths available. For example, this length, this is 16, this is 16, this is 12, 12, 12, and this 16. So you sum all of these, it will become 116 feet, right? Similar for the exterior walls, you have to calculate the total length available for the strip, which comes out to be 168 feet, And again, you have to calculate similarly for this, for example, 3 times 16 and 3 times 12, again 3 times 16 and 3 times 12. So this is the available strip length, and you have to calculate for your project accordingly, right? So the available strip length for the exterior wall, it is 168. So how do we calculate the width of the strip? Because if I show you in here that, for example, you have already decided that you want to strip like this. So for the interior, the total length is this, right? This is the length. So what will be the width of this strip B? So this is our aim, to find this B in order to design this wall footing, right? So for this, you have to divide the total reaction of the interior wall, which is 750, and then you have to divide it with the allowable bearing capacity into the available strip length, right? So if you do this calculation, it comes out to 2.9 feet. So we will take B1, which is the width of the strip for the interior walls, is 3 feet, right? Similar for the exterior walls, you have to divide the total reaction by the allowable bearing capacity into the length of the strip, and it will give you 3.007. We can round out into 3 feet as well. So for the both interior and exterior, the width of the strip comes out to be 3 feet, right? So this is how you calculate the width of the wall footing or strip footing. So this is the overall procedure. In case of the RC buildings, there will be no this much reactions. There will be some, for example, there will be a column, there will be a column. So if you want to give a strip in this, so you have to sum the reaction of this column, this, and again, similar procedure will be carried out to calculate the width of the strip. Right, so the next step is to draw these strips, and for the interior and exterior, these are the same, which is the 3 feet. So you can draw the beams in 36-inch offsets, and later on you can delete that, right? And you have to click in this direction, again in other direction. So it will draw the, so if there is a boundary, for example, this wall is at the edge for, so you can draw the overall width of the strip in the overall in this direction. For this example, we are taking on the at the center. So for this, you have to draw this and at this point, right? So this is the interior. For the interior, you have to again I think this should be 18 inches, right? So the overall width is 3 feet. This should, because we are using the center, so this is 18 inches, right? So it should be like this. So this is how you draw the overall strip footing. Right. So now these is being drawn. So now you can have to select all of these and go to edit and divide these frame at the intersection of each other. So it will divide that. So now you can draw your footing. Initially, we will take 12 inches, and we will see later on how we can change that. So you have to draw the strip like this. right? So this is how you will model the strip footing, and let us delete that beams. Right, so this was the overall procedure for the modeling of the wall footing, right? The next step is the thickness of the footing. As you know that the strip footing is a one-way slab, and the minimum thickness of footing is per ECI 31814 as defined in section 13.1.2, which is 6 inches. But the limitation of the one-way slab is also applicable on the strip footing, that it says if it is simply supported, the minimum thickness should be L by 20, or one end continues or both end continues, like, right? So in our case, it is simply supported, because the if you invert these footing, it becomes the slab. For example, this is the strip going, and if you place the walls over here, so it becomes the simply supported. It is not fixed, right? So if it is fixed with a beam or column, then it becomes the continues at one end and continues the other end. But it is actually the simply supported. Actually, it is both end continuous, but we will take it is a simply supported in order to get the maximum thickness for the footing, right? So in our case, the length, maximum length is 16 feet. And if you divide 16 into by 20, or divided by, or multiply with 12 to change into inches, so it comes out to be 9.6 inches. So we will take 12 inches or 15 inches, but let us take is 15 inches, because there is no issue of punching. So you can take any desirable thickness, but you have to satisfy the minimum requirement of the ACI. Right, the next step is to define the subgrade modulus to represent the soil, and it is the same formula, same procedure, but the allowable bearing capacity is different this time. So you have to multiply 12 into 3, it is factor of safety, and you have to multiply with the 2204 for in pounds, so it comes out to be 79344 pound per cubic feet, right? And then you have to assign these springs to the footing. You can assign this in ETAB, and you can also transfer it into the safe, right? So for this, again, you have to run the analysis, and then you have to export this file into the safe, and then you have to work with the design of the footing in the safe, right? Again, the next step is to export it to save as a F2K file, and then confirm the loads which is coming from the walls. This is the overall procedure from the ETAB. You can also insert load on the footing manually to calculate the overall loads coming into a specific wall, and then you have to draw the specific strip and then apply the load manually on that wall as well. Right, so this is done. So when you have to export it is a story as 2K file, and then again it is base, and all of these load combinations are selected. And again, then you have to go to the wall footing, and then you have to save it, right? Let me call it model 1, and then you have to export that file into the safe again, right? So let us go to the import to file, and let us model 1, right? So this is the model, and then you have to, the next step is to define the subgrade modulus for it. So you have to go to the define subgrade modulus and click on new property, and give the name as 1 TSF, and write the 79344 1 cubic feet. This is the subgrade modulus, and click on OK, and click on OK. Right now, assign this support data soil properties 1 TSF to this soil. Right, so now you can run the analysis, and you have to insert. Let me decide the thickness. Define the slab property, which is 12. We will take 15. You can also take 12, because the minimum thickness for the slab as per ACI is 9.6 inches, and we will take is 15 inches. Right, so the analysis has been run. If you click on the show punching check, so there is no check because walls are running around the strip, and here these are the walls columns in which it is showing you the not reflected because you are not model, we haven't modeled any auxiliary footing for these columns, right? So this is the overall procedure for the modeling and importing and exporting from the ETAB into the SAF and all of these. Now the next step is to design its reinforcement, and for the reinforcement again as per ACI 1814, it should be designed as not two-way, it is actually one-way slab, and it is defined in section 13.3.2 that the one-way slab, one-way shallow foundation, the design and detailing of one-way shallow foundation including strip footing, combined footing, and grade beams shall be in accordance with chapter applicable provision of chapter number 7. And chapter 7 is about the one-way, and chapter 9 is about the beams, which we have designed in the grade beams means the strap beam, it is also called as a grade beam, right? And it is says the combined footing. So if the width to the length to width ratio is greater than 2, so we will be designing the combined footing as a one-way. If it is equal less than 2, it will be designed as a two-way slab, which we did in the last session, right? So this is how you will design. And first of all, you have to check the minimum reinforcement for the design of the wall footing. And as per ACI 1814, the minimum reinforcement for the one-way slabs or footing is defined in 7.6.1.1, that this much reinforcement should be provided if the model or the requirement is less. And it says if you are using the grade 60 less than grade 60 steel, so only this equation is applicable. But if you are using the grade 60 steel equal to greater than the 60 grade 60 steel, so these two equations are applicable, which I think are the same for the two-way slab, right? So in our case, Fy is again 60,000 psi, and if we take H as 15 inches, right? So it will become 0.0018. So Fy will cancel with the 60,000, and it will become 15. So let's calculate it. Right? So it will be 0.0018 into 12 for per strip per footing, and then it will be the 15. So it comes out to be 0.324 inch square per foot. It is 0.324, right? And the next equation is the 0.001 for AG. It is 12 into 15. It is 0.0014 into 12 into 15. So it is 0.252. 0.252. So this is the governing equation. This much reinforcement should be provided if the safe result is less than this much reinforcement, right? So let's go to the safe, and the design, click on the design, click the finite element based, and check the bottom reinforcement, right? So this is the bottom reinforcement, and it says 0.05 inch square per foot, which is very less reinforcement, right? So if I impose the minimum, so it will increase to 0.3, right? So here it is 0.26, which is, in our case, it is this equation, and for the other location, it is 0.3. It will give you different reinforcements as per the requirement, right? So this is the reinforcement it is asking. right? This is the reinforcement is greater in this location because of the earthquake forces, because if you design it only for the gravity, so these loads will be decreased. Let me show you so you can learn, right? So if I remove all of these load combinations, if I design it only for the gravity, which is 1.d plus 1.2d plus 1.6, and if I click on OK, and if I run the analysis again, so the reinforcement will be very, very, very less, because the more reinforcement it is asking because of the earthquake forces, and earthquake forces produces more reinforcement means more unbalanced moments. You can see in case of the all load combination, it was almost 0.9 or 0.8 inch square per foot, but now you can see it is 0.324, right? It is very, very less. So this is depend upon the designer whether you are designing your structure for the earthquake or not, right? If you are designing for the earthquake, so it will ask more reinforcement. So this was the design for the gravity, but normally you want to design it for the earthquake to be on the safe side. So you have to include the all load combinations, right? So this is how you can design your building only for gravity loads to exclude the load combination, including the earthquake forces, right? So the more reinforcement you are getting, this is because of the unbalanced moment produced by the earthquake forces, right? Now you can see it is jumped into 0.8 or 0.7. It was previously on the gravity load, it was 0.3 or 0.2, right? So now let us go to the design phase, and let us use number 4 bar at the rate 12 inch center to center and click on apply, right? I will recommend you for the design purpose that do not check this impose minimum, right? Because it will impose the minimum criteria for the top and the bottom as well, but as per the code the minimum criteria is for the both, right? So if the minimum reinforcement is 0.32, so then you have to provide 0.32 in dividing by 2. For example, it is 0.3, so 0.15 you will provide at the bottom and 0.15 you have to provide at the top. But software do not do this. It apply the minimum criteria for the bottom individually, and for the top individually. It will become uneconomical for the design purpose, right? So the number 4 at the rate 12 is not working, because it is working in some places, but this is the portion in which the unbalanced moment is more. So you have to go for the number 4 at the rate 6 in center to center. So again, in the this is the direction 1, right? So let me show you the directions as well, right? So this is the, for this long strip, this direction 1 is the, as per the this combination, this is direction 1, this red one, and for the this strip, this is the direction 2. So the main reinforcement you will be providing is in the direction 1, and for this strip this will be in direction 2, right? So in direction 1, the strips you will be providing this, like in this direction the reinforcement will be like this, and it is number 4 at the rate 6 in center to center, and it is working in some places but is not working in these 2 strips because of the unbalanced moments. Let us check in direction 2. In direction 2, it is still working in some places, but it is not working in some of this region. It's still asking about the reinforcement. It is very, very less reinforcement. If you can see, it is 0.0062, right? So the value is 0.0062. If you want to give the reinforcement, so if you use number 2 bar, right, at the this much reinforcement, and if you multiply with the 12, so you have to provide number 4 bar at the rate 386 inches center to center, right? So this is negligibly small. So normally we neglect this much reinforcement in our model. You can also design the slab in the ETABs as well, but normally the designers use the SAFE for the design of the footing and the slabs, right? Similar for the top, if you use number 4 bar at the rate 12 in center to center, it is working in some places, but it's not working in other places, and it's still asking very, very less reinforcement is 0.01 inch square per foot, right? So again, if you use this 0.01 inch square per foot, and if you use number 4 bar with this much reinforcement multiply with 12, it changes. So you have to provide number 4 bar at the rate 240 inches center to center. So it is negligibly small. You can neglect that as well, right? So this is how you calculate or decide the footing. So if you provide number 4 at the rate 6, so now it is very less in this direction and the less in the direction, which is almost working, and you can neglect this much reinforcement, because if you go for the number 6 bar for residential building, so it is not economical or not recommended, right? You can also provide in the critical section. If you want to provide only in this region, in this critical region, you can provide number 4 at the rate 3 inches, but not less than this much reinforcement. Now you can see the reinforcement has been disappeared, and similarly for the other direction as well. Similarly for the bottom, if you want to provide, if you are a new engineer, a new designer in the field or in the consultancy, and if you are not feeling safe, so you can move into the number 6 bar as well, and you have to provide this. So you can see that this, it will still ask some reinforcement, although you have provided number 6 bar, there is 6 in center, but still it's asking some of the reinforcement. So one solution is that you give the large number of bar, and you can increase the area if it is possible. So if you increase the area, so it will give you less reinforcement. Another check is you increase the thickness of the footing, right? So if you increase from 15 to 18 inches, so this will decrease the amount of reinforcement required as per the demand. So if the reinforcement is very high, and if it's asking number 8 bars or number 6 bar for the residential building, you have to increase the strip area, or you can increase the thickness of the footing, right? So for this case, I have increased this area from the 3 feet to 5 feet. In some cases, it is 6 feet, because I have the available plot area. And if I give the number 6 bar at the 6 center, it becomes very uneconomical for me. But if I increase the strip area and keep the thickness into 12 inches, that will work for me in number 4 at the 6 center, right? So now I have increased or doubled the bearing area from 3 feet to 5 feet, almost double. So this is the 5 feet strip. So now it is working for me with the number 4 at the rate 6 in center to center in direction 1 and as well as in direction 2, right? And the thickness of the footing is 12 inches. So normally the thickness governs, or the economy is related in the case of the strip footing is the thickness. So if you can keep the thickness as much as small or minimum, so it will give you the economical design, right? So I have increased the thickness of this footing into the width of the footing to 5 feet, and I have reduced the thickness into 12 inches. So the economy wise, it is economical as compared to 3 feet width and 18 inches thick, but still it was asking about number 6 bar. Similar for the top, if I use number 3 bar at the rate 6, so it is working, right? You can see there is a big difference in the economy in case of the steel, because you know the steel is very expensive nowadays, so you must try to save the steel as well, right? So the conclusion is that for the economy point of view, you have to provide for the bottom, you have to provide number 4 bar at the rate 6 inches center to center, right? But for the top, you have to provide number 3 bar at the rate 6 inches center to center. These are the actually the short direction, which is the main reinforcement, right? So let me write it in the short direction, or it is actually also called a main direction, main bars. Short direction, main bars, but with the width equal to 5 feet, right? If you keep the width is equal to 3 feet, then more reinforcement will be required and it will become uneconomical. So this is how you will do the different case studies to make your structure economical, right? So we have taken this as a 12, so this will also decrease into the, so this is the 15, so it will become 12, and it is also become 12. So it is 0.25 and it is 0.2. So I have done this intentionally to show you how you will do different case studies to make your structure economical, or play with the thickness or width of the footing, or play with the reinforcement to make it economical, right? So this was the whole story about the main reinforcement. So this session is about to end, so let me reproduce the link, and you will start about the design of the reinforcement in the other direction, the long direction, right?